So the next property of the Poisson process that we will talk about is its relationship to a Bernoulli process. Take a Poisson process at rate lambda and discretize time in small chunks. Show that as the chunk size, delta, goes to 0, the Poisson process can be approximated by a Bernoulli process. Let's do this. Okay, so this is time. And I discretize it with constant small intervals of size delta. Okay. Now, what is the probability that I get no arrivals in time delta, in an amount of time delta, of size delta? What is that? Well, the original Poisson process has rate lambda. Okay, the arrivals are falling in at rate lambda. The idea is to make delta small such that in every delta interval there will be at most one arrival, either one arrival or 0. The probability that there are two arrivals is negligible and small as delta goes to 0. Let's show that that happens. The probability that there are no arrivals, first of all, is lambda delta to the 0, e to the minus lambda delta over 0 factorial. What is it? It's e to the minus lambda delta. Now, as lambda delta becomes small, this is approximately 1 minus lambda delta. In general, we can write this as 1 minus lambda delta plus little o of delta. This little o notation means this thing, these terms in little o, go to 0 as delta becomes small. Okay, so this is approximately 1 minus lambda delta. Okay, so do you remember that in general, if you have e to the, anyway, e to the x, and x is small, it's roughly approximated as 1 plus x. Okay, so what is the probability that there is one arrival, exactly one arrival in a delta interval? What is that? Lambda delta to the power 1 e to the minus lambda delta divided by 1 factorial. So this is roughly, well, first of all, in this notation, it's lambda delta plus little o of delta. Why? Because I'm multiplying lambda delta with all the terms here. And lambda squared delta squared is a term that goes to 0 faster than lambda delta when delta is small. So this is approximately lambda delta. You see this? If you want, let me write this more openly. It's lambda delta times 1 minus lambda delta plus little o of delta. And this is lambda delta times lambda squared delta squared plus small o of delta. But this term, as lambda is getting small, this is getting small, as delta is getting small, this is getting small faster. Okay, so this, because if you divide this by delta, what you get is still on the order of delta, which is going to 0. So this is also little o of delta. Okay, so basically what is the point here? The point is that the probability that there are no arrivals is roughly 1 minus lambda delta and the probability that there is one arrival is roughly lambda delta. What is the probability that there are bigger than or equal to 2 arrivals? It's approximately 0. Why? Because it's going to be on the order of delta, the law of delta. So, what do you see here? Let's, rephrase this. We focus on one interval like this. The probability that there is one arrival is lambda delta. The probability that there is no arrival is 1 minus lambda delta. Okay? Let's call this P, and then this will be 1 minus P. This is a Bernoulli process. In each little chunk of time, there is an arrival with probability P, no arrival with probability 1 minus P, and the possibility of more than one arrival is non-existent. This is becoming more and more correct when we take delta to 0. So we obtained a baby Bernoulli process. Okay? We showed that the Poisson process reduces to a baby Bernoulli process. Can be viewed as a baby Bernoulli process. Why do I call it baby? Because, well, you need to make the chunks very small. Okay? So, in an actual, anyway. So, okay, in a Bernoulli process, what happens in the next interval of time should be independent of any other interval of time. Is that satisfied as well? Yes, because the Poisson process has the property that arrivals in any two disjoint intervals are independent of each other. So, okay, so basically we can view the Poisson process as the limit of a Bernoulli process, which is nice. In fact, this gives us a third definition for the Poisson process. Namely, the Poisson process is a process in which if you take a delta amount of time of size delta, the probability of an arrival is lambda delta plus little o of delta. The probability of no arrival is 1 minus lambda delta plus little o of delta, and the probability of more than one arrival is roughly 0, or little o of delta. If you do this, and if you also say that successive chunks of time are independent of each other, you get exactly a Poisson process. Okay, so this is a third way of defining the Poisson process, which is also useful sometimes. Okay. So in the next property, we're going to apply this. Okay. We'll apply this to show what happens when you split a Poisson process independently. Okay. Here's the example. It's an example, but it's essentially the result itself. Show that when we send each arrival of a Poisson process at rate lambda to a process A with probability P and process B with probability 1 minus P, the resulting processes A and B are Poisson with rates P lambda and 1 minus P lambda. Okay. Note also that processes A and B are independent of each other. This is unlike the Bernoulli case. Okay? So if you remember, last time we split the Bernoulli process. What did we do? Arrivals, so basically we look at discrete time. For example, every minute a student walks in with probability P, and there is no student with probability 1 minus P. Okay? And every minute I toss a coin. If the coin is heads and a student comes in, I let the student in. If the coin is tails when the student comes in, I send the student to the other classroom. We showed that the number of arrivals in the two rooms, the process of arrivals in the two rooms are Bernoulli processes, but they are not independent. They're not independent because, for example, if I know that there's an arrival in this room with this minute, at this minute, then there cannot be an arrival in the other classroom. Okay? Because, I send the student either here or there. Okay? So they are dependent. What are the rates of the split Bernoulli processes? If the original rate was P and my coin toss probabilities are, heads probabilities are, then the rates are PR and P1 minus R. Okay? This is going to be similar, except here when you split the Poisson process, you get two independent Poisson processes. This is useful because, for example, in networks, if we randomly route packets this way or that way, and the packets were originally a Poisson process, we know that the arrivals in the routers that we route to will still be Poisson processes. So that's useful. Anyway, so I have my arrivals. And I send them to either process A or process B. So this arrival is sent to A, this one is sent to B, this one is sent to B, this is in A, this is in B, etc. Okay. Now we need to show that the inter-arrival times x sub A in the A process are exponential at rate P times lambda. So the original process is at rate lambda. Every arrival is sent to process A with probability P. Okay, with probability P, it's sent to A, and with probability 1 minus P independently, it's of every other arrival, it's sent to process B. Okay, we need to show that XA is exponential at rate lambda P. Is the splitting clear? So when an arrival comes, it's sent to the A process with probability P. It's sent to the B process with 1 minus P. So the process A is a decimated version of the original process. Decimation rate is P. But we just need to show that the inter-arrival times are exponential. This is going to be an exercise of something that we have not done in this class so far, in this section, which is thinking about a random sum of random variables. So here's what I mean. Let x1, x2, x3, and so on be the inter-arrivals of the original process. So, what is XA? Given that I just had an arrival in the A process, X sub A is the amount of time it will take me until the next arrival into the A process. Okay? But for that, I will need to wait for the next arrival to the original process that will get routed to the A process. Okay? Well, if the next arrival to the original process is sent to A, then I need to wait for just one interarrival time. But if the next arrival is not sent to A, and the second next is sent to A, then A will be the sum of x1 plus x2. So in general, xa is the sum of an arbitrary, a random number of interarrival times from the original process. You see this? So let me sketch this. Sketch an example of this. Suppose this is the original process, and this is the A process. The original process has some arrivals. This is x1, this is x2, x3, x4. Okay? Now, suppose I start by looking at the first arrival in the A process. Now, suppose this one is sent to B, and this one is also sent to B, and this one is sent to A. Then this is the first arrival into process A. What is this amount of time? This amount of time is x1, this amount of time is x2, this amount of time is x3. And together the sum gives me xa, interarrival time in the A process. Is this clear? I don't know how many of these there will be. What is the distribution of the number of... It's geometric, right? Because n is the number of arrivals in the original process up to and including the first one that's sent to A. Okay? And let me write this down. Number of arrivals in the original process up to and including the one sent to process A. Okay? So n is geometric with parameter p, because the probability of being sent to A is p. Yeah? So the probability that n is equal to k is 1 minus p to the k times p. No, 1 minus p to the k minus 1 times p. Okay, so n is geometric and the xi's are exponential. We have this strange thing which we have not seen in this course before. So how do we think about this? It's a random sum of random variables, because the number of random variables we're summing is also random. To start, let's first think about the expectation. Let's think about the expectation. The expected value of the sum I from 1 to n, x sub I. We can use iterated expectations, right? If n was given, I know exactly how to do this. So compute the expectation over n of the expected value of the summation I from 1 to n, xi, given n. What am I doing? This is iterated expectations. Okay? Given n, the inner expectation is easy now, because if n is given, then n is not random anymore. So this would be n times the expected value of x1. Why? Because the xi's are all identically distributed. So I'm talking about the expected value. Well, to be perfectly correct, I should keep n in the conditioning, of course. Okay? So this is the expectation over n of n times the expected value of x1 given n. But x1 is independent of n, so I can replace this by simply expectation of x1. x1 is just one inter-arrival time from the original process. It doesn't matter for x1 how many of these I'm adding. Anyway, this is simply expected value of n times expectation x1, and expectation x1 comes out expectation of x1, expectation of n. Okay? So this is very intuitive. The expected number of a random sum of random variables where the number of random variables n does not depend on the random variables themselves is given by expectation of n times expectation of the random variables you're summing. Here we use the fact that the xi's have the same distribution, they're identically distributed, and they don't depend on n. Okay? So, okay, but that's very nice. That at least tells us that the expected inter-arrival time xa is expected n times expected inter-arrival time of the original process. What is that? So expectation of xa is expected n times expected x1 or xi. What is this expectation? That's 1 over lambda. What is this expectation? N is geometric with parameter p. So this is 1 over p. What do I get? 1 over p lambda. That's encouraging because it's consistent with what we're trying to prove. We're trying to prove that xa's are exponential at rate p lambda, and that's consistent with that. Okay? So, in order to show that xa is exponential, I'm going to apply transforms. So let's make some room here. I'll simply take the transform of xa. mxa of s. That is expectation of e to the s xa, which is the expectation of this, e to the s summation xi, I from 1 to n. Try to follow this because this will go somewhere really interesting. So what is next? Also, it's a good exercise of everything we've learned in the class. Now, what do I do next? What do you suggest? Okay. Expectation of product e to the s xi, I from 1 to n. Xi's are independent, right? They are independent. However, there's a problem. N is a random variable. So I need to apply again iterated expectations. Expectation over n of expectation of the product given n. Expectation given n. Now I can simply write this as, well, what do I do now? Move the expectation inside because xi's are independent. So this is the expectation over n, the product I from 1 to n of expected value of e to the s xi given n. But the xi's don't depend on n, so I can just say this is expected value of e to the s xi. Okay? So we're almost there. Let's see. I have xa of s equal to expected value over n, product I from 1 to n, expected value of e to the sxi. Now, what is this? It's the same thing for every I, because the x's are identically distributed. So this is mx I of s. So I simply have the expectation over n mx1 of s raised to the power n. Let me draw a line like this. So, excuse me? Very nice. It's like the moment generating function of n. Okay? Because what is the moment generating function of n? It's the expectation of s to the n. Oh, I'm sorry. E to the sn. What do we have here? Expectation of something raised to the power n. So this is like the moment generating function of n evaluated at e to the s being equal to mx1 of s. So wherever you see e to the s, you plug in mx1 of s. Okay. So let's repeat. When we have a random sum of random variables like this, and the random variables that we sum are identically distributed and they're independent of n, then we have mxa of s is equal to mn of s evaluated at s equals, e to the s equals mx1 of s. What does, let's apply this. It may seem very confusing when written like this. Does anybody remember, let's try to do our best to follow. What is the moment generating function when n is geometric with parameter p? Do you remember that? I don't even remember that, but I'll try. P e to the s over 1 minus p e to the s. Can anyone check? I think so. Let me check from my notes. I guess I have notes. Oh, I'm wrong. 1 minus p e to the s. 1 minus p e to the s. This is the moment generating function of an exponential with rate or parameter p. Okay, so I'm to find the moment generating function mxa of s, I need to use this, and wherever I see e to the s, plug in the moment generating function of x1. Okay, so p times moment generating function of x1. What is that? Exponential with rate lambda, so it's lambda over lambda minus s. Lambda over lambda minus s divided by 1 minus, what do we do? 1 minus that, which is s over lambda minus s. How about that? Oh, what am I doing? 1 minus p, I think I taught too much. I need a vacation. I decide to take a vacation after this class. How about that? Okay, 1 minus p times lambda over lambda minus s. Okay, so let's simplify this. It's p lambda over, what do you have? P lambda minus 1. No?
Yes, 1.
Okay. This gives me lambda minus s, and I have lambda here. The lambdas cancel, and I have p lambda here. So p lambda minus s. Oh, that's nice. That's neat. Why? Because this is the transform of an exponential. Transform of an exponential at rate p lambda. Okay? So we have just proved that xa, the intervals of the A process, are exponential at rate p lambda. Okay? So now you can believe me that when we randomly split a Poisson process, we get a Poisson process. At least the interarrival times are exponential. And we get the independence of interarrival times by the independence of the interarrival times of the original process. Okay? Great. So we did two things at the same time. We showed the splitting result for the Poisson, and we also talked about how we handle a random sum of random variables. Final thing is merging Poisson processes. By the way, we have not proved that the resulting split processes are independent. So if you're interested, you can read about that in the textbook. That's an end of the chapter exercise problem in the textbook. Okay. So show that when we merge two independent Poisson processes at rates lambda sub a and lambda sub b, we get a Poisson process at rate lambda sub a plus lambda sub b. Hint, consider two light bulbs with exponential lifetimes running side by side. What do you think this has to do with the example? Find distribution of the time that the first one burns out. Interesting. Okay. First, I'd like you to remember the Bernoulli process merging result. I had two processes at rates P1 and P2, and when I merged them, I record an arrival when there's an arrival in either process. And the rate of the resulting process was P1 plus P2 minus P1, P2. Here, we don't have that P1, P2 term. Simply, if the original process has rate lambda 1, if the first process has rate lambda 2, the second process has rate lambda 2, when we merge them, we get the merged process at rate lambda 1 plus lambda 2. Why? Because the probability that the both processes have an arrival at exactly the same time is 0. We are in continuous time. And the probability that in this delta interval, both this process and this process have an arrival at the same time is proportional to delta squared, which is little o of delta, which becomes negligible as delta goes to 0. So the original process, the sum process has rate lambda plus lambda 2. But we'll not, rather than use the baby Bernoulli approximation, let's prove this using racing exponentials. Okay? So as the final thing we do in this course, we address racing exponentials. Okay, so I look at a certain time, and I will wait for the next arrival. Okay, show that this time, I call it x merged. show that this is exponential at rate lambda 1 plus lambda 2. Now, I record this arrival if, this is the first arrival to either process. So if this process has an arrival first and this process has an arrival later, I will record this as the first arrival in the merged process. Why? Because this is how we merge. Suppose these are the arrivals of the first process and these are the arrivals of the second process. All these become the arrivals of the merged process. Okay? So the probability that X in the merged process, X merged, is bigger than T, is the probability that the minimum of X1, X2 is bigger than T. Okay? So look at time T. Look at time T. This is X1 and this is X2. Okay? I record an arrival when the first one hits. So I'm dealing with the minimum of X1 and X2. Well, if the minimum is bigger than T, these are lifetimes of two independent light bulbs that are racing. Right? The minimum is bigger than 2 only if both are bigger than 2. And I can multiply the probabilities because they are independent. And this is e to the minus lambda 1t. This is e to the minus lambda 2t. So I get my result, lambda 1 plus lambda 2. So the merged process has interarrivals that are exponential at the sum rate, which makes sense. For example, if there are bus arrivals happening at rate 1 bus per 10 minutes, there are also dolmuş arrivals that are happening at 1 dolmuş per 7 minutes. And you can take either one. You're waiting there, you'll get the first vehicle that comes by. So for you, the vehicle arrival process is at rate 1 over 10 plus 1 over 7. Maybe these numbers aren't exactly great. How about let the dolmuş process also be at rate 1 over 10. Okay, so 1 over 10 plus 1 over 10 makes 2 over 10. So you expect to wait for 5 minutes, right? Okay. So that's what happens when we merge two independent Poisson processes, and this is the end of our discussion of the Poisson processes. Yes, please.
Şimdi burada x1 eğer x2'den küçükse x2 alacağız. Eğer x2 büyükse x1 alacağız değil mi? X1'den
Exactly. We record the first
bu şöyle yapabilir miyiz?
arrival.
P işte x1 büyüktür t işte çarpı p çarpı x1 küçük x2 artı işte p x2 büyük t çarpı x2 küçüktür x1.
You would have to then integrate over their PMFs and PDFs, and eventually you'll come to the same result. Right. Okay, thank you for your attention. It's been a nice course. Good luck in your future studies, and good luck in the finals as well.